Okay, everyone, welcome back. So in this video, what we're going to do is we're going to discuss halogenation of alkanes in general. Now, we've already discussed free radical halogenation of methane, which is also an alkane. So that's kind of like the first video that you should watch, because a lot of the nitty-gritty and the fundamentals were discussed in this video. Now, we're basically going to build on that content and information in this video. And we will use one alkane, and then we will basically see some trends that we will be able to generalize then, okay? So halogenation of alkanes. That's the topic. Let me switch out this pen, okay? And we're going to look specifically at chlorination and bromination of propane. And we'll try to see as to what else can we learn about this reaction, like the halogenation reaction, based on propane as an example of an alkane. So what else can we learn in terms of like new concepts? What are some things that we can basically retain that would be applicable to other molecules? So propane is the 3-carbon alkanes, CH3, CH2, CH3. So if I have to chlorinate propane, the reaction is pretty similar to what we did for chlorination of methane. What I would do is I would react this with Cl2, and you would need heat or light. So for doing this reaction, you need energy. And we know why we need the energy, because we have to get the reaction initiated. The chlorine has to dissociate, break, to give you the radical intermediates. Okay, now the question here is, when we look at propane, it's unlike methane now. Methane had 4 hydrogens. They were all identical. They were all of the same kind. Those were methyl hydrogens, or based on a methane. Okay, so methane hydrogens. But notice how propane, or for that matter, any other molecule beyond methane, and I guess ethane to some extent, because ethane would also have only one kind of hydrogens, but any alkane beyond methane and ethane has different kind of hydrogens here. So in propane, we have the methyl groups, and the hydrogens on the methyl groups can be classified as primary hydrogens. So that's something that we've already discussed. So these are primary hydrogens. Similarly, the hydrogens on the CH2, these are secondary hydrogens. And remember, we use this primary and secondary symbol to denote those hydrogens. And that's what we will use going forward. So there are 2 different kind of hydrogens in this molecule. There's primary hydrogens and there's secondary hydrogens. And from the structure, we also see how many of these we have. I think we can quantitatively say that there are 6 primary hydrogens, 3 here and 3 over there. And then we have 2 secondary hydrogens. So when we chlorinate propane, I think we should expect 2 products. One where the primary hydrogen is replaced, and the other where the secondary hydrogen is replaced. So I think we can come up with 2 products. One's going to be CH3, CH2, CH2, Cl. So this is the product where one of the primary hydrogens of these 6, because remember, they're all primary. So one of these primary hydrogens is replaced with a chlorine atom, okay? And we will get another product which is that. Now that's the product when one of these two secondary hydrogens is replaced by the chlorine atom. So we can expect two products here. So now if I were to like ask you, like what would be the ratio of these products, which of these two products you would think you would form in a higher amount? I think based on statistics, since there are three hydrogens or total of 6 primary hydrogens, and there's only 2 secondary hydrogens, I think statistically I would tend to I would hypothesize that, you know, I should have more of this product because I could replace any of the 6 primary hydrogens and it would give me the same product. Now, also realize that whether I write the product like this or I write the product like this, these two are the same molecules, because now that we know nomenclature, this is 1-chloropropane. This is also 1-chloropropane. That is 2-chloropropane. So the product here is 1-chloropropane, and then we have 2-chloropropane. So those are our 2 product possibilities. So what we were saying is, statistically, we would hope that we will get more of the 1-chloropropane and less of the 2-chloropropane. But the actual ratios in terms of percentages is we get 40% of the 1-chloropropane product, we get 60% of the 2-chloropropane product. And so there must be something else here, and we will get into that later, you know, but that's the ratio, product distribution here. Now, if we did bromination of propane, okay, so if I take propane and if I react with bromine, and again, you need heat or light, although for doing this reaction. In fact, bromination sometimes need a little bit of heat and light, actually. It's beneficial, and we will see why. So bromination, heat or light is fine. If we do this, I think again, we would get 2 products, or we should expect 2 products. 1 bromopropane plus 2 bromopropane. Okay, those are the 2 products we expect. Now again, so the question is, okay, what would be the ratio here? Okay, we get the 2 products. In case of chlorination, it was 40% and 60%. In case of bromination, it turns out the ratio is 3% and 97%. Okay, so you get almost exclusively the 2 bromopropane. Okay, and again, I want to connect this, realize how we get these 2 products. We get the 1 bromopropane by replacing one of the primary hydrogens. We get 2 bromopropane by replacing one of the secondary hydrogens. Okay, so that's how we're getting to the product. So looks like in case of the bromination reaction, somehow this bromination at the secondary position is favored. It's almost exclusive, you know, like 3% is very tiny. And so for this reason, what we say is that bromination of alkanes is a selective reaction. Okay, it's a selective reaction, and this is a very important thing to remember, and we will dig through like a lot of the details as to why this happens, but it's very important to remember that bromination of alkanes is a selective reaction because it gives us exclusively like a major product. It gives us a major product. Now you could argue that, okay, there is a major product here because we have 60% of the 2-chloropropane and there's only 40% of the 1-chloropropane, but realize that 60 and 40, that's still like a ratio which if you're in a lab doing this reaction, you would have to do some sort of a purification, like extensive purification to separate these out. Whereas here, it's very tiny bit of like one component. It's almost pure, exclusively pure, you know. So 3%, if we did an NMR or something on that, that's like almost close to the detection limit. You may or may not. You can get those numbers, but you know, it's like very tiny. So the reaction itself gives us like a major product in terms of what we're doing here. Okay, so what we'll do is, now that we have the equations here, we know what happens in a chlorination of propane or in a bromination of propane. We will dig deeper into these reactions and we'll try to see why is this like that, okay? Why does this happen like this? So we will work through the mechanism, because again, when we have a reaction, the reasons why something happens, it's always in the mechanism of the reaction. So we'll go into the mechanism of the reaction to understand why this happens. Why do we get a selective bromination, chlorinations not so much, okay? So that's where we're going, and we will do these one by one, okay? And the mechanism itself is very similar to what we did for bromination, for the halogenation of the free radical halogenation of methane. So, and we will do chlorination first, okay? So chlorination of propane. This is what we're going to talk about. Okay. Now, this particular case, again, any free radical reaction starts with an initiation process. Okay, that's where it starts. So the first step is initiation. If you're doing chlorination, then this step is where the chlorine fragments with input of energy to give us the chlorine radicals. So we will make 2 chlorine radicals from a chlorine molecule. So this is again single electron. So the fishhook arrows is what I'm using here. Okay. Once we have the initiation, we've made our reactive intermediate. The next step is propagation. Okay, so the propagation step, the chlorine radical, and I'm going to write the first propagation step here. The first propagation step. So chlorine radical reacts with propane. Now, remember that in propane, we have 2 types of hydrogens. There's primary hydrogens and there's secondary hydrogens. So it could react with either one. So we're going to show both of them. So let's assume that in this first step, it is reacting with a primary hydrogen, one of the 6 primary hydrogens. So it shows that. So the chlorine brings its electron, that bond fragments, hydrogen brings its electron, very similar to what happened in the methane case. So the H and the Cl combine, and this would give us HCl plus a primary carbon radical. So that's a radical on a primary carbon. So that's a primary carbon radical. So that's one possibility. The other possibility here is that the chlorine radical that chlorine radical now reacts with a secondary hydrogen instead. So to show that, I'm going to say we have propane, but we want to focus on this secondary carbon hydrogen bond. So the chlorine is reacting with the secondary radical. So the chlorine brings its electron, the hydrogen brings its electron, the other electron goes back to that carbon. Okay, again, all of these are single-headed fish hook arrows. That's what I'm drawing there. Okay, and at the end of this, this would give us HCl plus, it's going to give us a secondary carbon radical. Now I don't have to put the radical here at the bottom. It's on that carbon, the secondary carbon. So I'm going to put that radical on that carbon. So these are two possibilities for the first propagation step. Okay, these are both possibilities for the first propagation step. Okay, now after this, we have our second propagation step. So in the second propagation step, if we start with the primary carbon radical there, that primary carbon radical can now react with chlorine. Carbon brings the electron. Chlorine fragments brings the electron. The other electron goes to the chlorine atom. And this would give us, the way I've written it, Cl, CH2, CH2, CH3 plus a chlorine radical. Okay, so that's the second propagation step. And notice how between the two propagation steps involving the primary carbon, in the first propagation step, we made HCl as a product, which is one of the products that we should be forming. And we made, in fact, I apologize because I left out HCl and HBr in the previous schemes that I had. So HCl and HBr should be products. And then the primary carbon radical reacts with chlorine to give the 1-chloropropane and the chlorine radical. Okay, so that's the second one possibility for the second propagation step. The other possibility using the secondary radical is that the secondary radical now reacts with the chlorine, cleaves, and it would give us CH3, CH, CH3, with a Cl plus a chlorine radical. So this should be the mechanism of how our products are formed. From the scheme that we saw on the previous page, how we make 1-chloropropane and how do we make 2-chloropropane based on this free radical halogenation mechanism. Okay, now that we have the mechanism, we're going to use, so I actually printed out the sheet for myself. This is the bond dissociation enthalpy sheet that's available on Blackboard now. So I've printed this out, and essentially what we can do is we can use the table to do the calculations for delta H for the chlorination of propane. So if we look at the first propagation step here, we are breaking now a primary carbon hydrogen bond. So on this table, first column at the bottom, these are all delta H, the bond dissociation enthalpies for primary carbon hydrogen bonds. And what I see is that the very first entry over there, now notice how that molecule that's drawn is not propane, it's ethane, but that doesn't matter because that's the bond dissociation enthalpy for breaking a primary carbon hydrogen bond. And the bond that's shown in this table is a primary carbon-hydrogen bond. I don't know if this camera would capture it, but this is a primary carbon-hydrogen bond, okay? And this is also a primary carbon-hydrogen bond. So we can use the same value. To a good approximation, they should be very similar, okay? So that number is 423 kilojoules per mole. On the product side, we have HCl, and we already had that number. This was 432, but HCl is a product. It's a bond that was formed, so it should be negative 432 kilojoules per mole. To calculate the delta H, all we have to do is add these two up. So I'm going to write the delta H here. This number is basically negative 9 kilojoules per mole. That's a negative 9. Okay, that's the delta H for that number. And then we can calculate the bond dissociation enthalpy for the second propagation step. You're breaking a chlorine and a chlorine. This is 240 kilojoules per mole. And then we made a bond between a primary carbon and a chlorine. So again, in the table, first column, bottom portion, there is an entry for a primary carbon-chlorine bond, and that number is 355 kilojoules per mole. So 355, and this is a negative number, 355 kilojoules per mole. So delta H for this step is the sum of these two, which is negative 115 kilojoules per mole. Okay, so it's negative 115 kilojoules per mole. Now, similarly, I can calculate the delta H for the other process, which is the formation of the 2-chloropropane. And to break a secondary carbon-hydrogen bond, which is what we're doing here, second column top, bonds to secondary carbon-hydrogen bonds, the energy required is 413 kilojoules per mole. And HCl is that same number, so it's negative 432 kilojoules per mole. Delta H, the difference between these two, so 19. So this is negative 19 kilojoules per mole now. So that's a negative 19, minus 19. And similarly, we can do it for this here. So to break the chlorine-chlorine, it's the same number, 240 kilojoules per mole. To make a secondary carbon and chlorine bond, it's negative 356 kilojoules per mole. Negative 356, which means delta H here is negative 116 kilojoules per mole. So 116, negative 116 kilojoules per mole. So those would be our thermodynamic calculations. And what we see here is, based on these numbers, what we see is the first propagation step in the chlorination of propane, whether it is the formation of the primary carbon radical or the secondary carbon radical, the first propagation step is exothermic. So compare it to the chlorination of methane, that was an endothermic step. So notice how it is not like a constant. It changes depending on the reaction, okay? So this is an exothermic step, and the second propagation step, whether you're making 1-chloropropane or 2-chloropropane, is also exothermic. Those are both negative values. Okay, so that's also a negative reaction. exothermic reaction, sorry. Now, we'll go ahead and do the same for bromination and see what sort of numbers we get, okay? So let's go ahead and do bromination of propane next. Okay, so for bromination of propane, that means we're talking about this reaction where actually I want to write this whole equation because when I wrote it initially I missed out that HBr. So what we're talking about is propane reacting with Br2 in presence of H nu or heat or light to give Br plus CH3 Br plus HBr. So that's the other product that's there. That's what I left out initially. HBr should be formed. So the hydrogen bromide is also formed. Okay, so that's the reaction that we're looking at. So again, to start out, in terms of mechanism, the first step is an initiation step. Okay, so the initiation should be now bromine fragmenting homolytically, and again you can use heat or light for doing this to give bromine radicals. So the bromine fragments homolytically to give bromine radicals. That's the initiation step. We made our reactive intermediate. Propagation step okay. Propagation step again has two possibilities because we need to make the 1-bromopropane and we also need to make the 2-bromopropane. So the first propagation step, our possibility is the bromine radical reacts with a primary carbon-hydrogen bond. The bromine brings an electron, fragments, brings an electron, the other electron goes to the carbon atom, and this is going to give us HBr plus the primary carbon radical. Let's go ahead and write the other possibility, which is bromine reacting with a secondary hydrogen. Secondary carbon-hydrogen bond. Bromine brings its electron. The hydrogen brings its electron. The other electron goes to the carbon atom. It's going to give us HBr plus the secondary carbon radical. And now we can write the second propagation step. Primary carbon radical reacts with another molecule of bromine. So see how this is kind of repetitive in terms of the number of steps, what we're doing. Okay, first the bromine fragmented, one of the bromine radicals interacts with the alkane to generate a carbon radical, then the carbon radical is reacting with more bromine. So this is pretty much what we've been seeing throughout, okay, for all of these mechanisms. So this brings an electron, bromine fragments, brings an electron, that would give us the 1-bromopropane plus more bromine radical so that it can go back and start the process again. Okay. And then the secondary carbon radical from there reacts with another bromine. So these are two possibilities of how we get to the two products. The secondary carbon radical brings the electron bromine fragments, and it gives us the 2-bromopropane plus bromine radical. Okay, so that's how we get to the product. And again, what we have done here is I'm showing you the initiation step and the propagation step. There are termination steps possible, but I'm ignoring those because realize those are not as important because they happen towards the end of the reaction. They don't contribute to the thermodynamics of the reaction. And they do not contribute significantly to how much product is formed or which product is formed, okay? Those are all minor things that are going on. So that's why we're focusing on this. So again, we have the bromination now, so we can work through the thermodynamics of the reaction. So focusing on the propagation steps for the formation of 1-bromopropane. This here, this is the dissociation enthalpy for the primary carbon-hydrogen bond, which was 423 kilojoules per mole. We use that same number in the chlorination case. Now on the product side, we have HBr forming. So from this table, I can see that the formation of HBr is negative 366 kilojoules per mole. It's not negative here, it is a positive number, but since it's formation, I'm using negative because that should be what the formation should be. And so based on that, delta H for this is the difference between these two, okay, or the addition of these two in some sense. Okay, so 423 plus 66 should give us 34 plus 23, which is 57 kilojoules per mole. Okay, and now in this case, this is a positive number. For breaking a Br bond, the energy required is 190 kilojoules per mole. And for a primary carbon bromine bond, the energy is negative 303 kilojoules per mole, which gives us a delta H of, oh, that's huge. So this is about negative 113 kilojoules per mole. You might want to calculate in case there's an error with my math, you know what I'm doing here. So, but this is about negative 113 kilojoules per mole. Now we can do the same for the formation of the secondary carbon radical. To break a secondary carbon-hydrogen bond, the energy was 413 kilojoules per mole. HBr is negative 366 kilojoules per mole, which means delta H is 34 plus 13. So that's about 47 kilojoules per mole. Okay, and we can finally calculate the energy for this, 190 kilojoules per mole. And for a secondary carbon bromine bond, it is 309 kilojoules per mole. which gives me a delta H of negative 119 kilojoules per mole. So those are all the thermodynamic values. And so based on this math here, what we see is that for the bromination of propane, the first propagation step is endothermic for both the formation of the primary carbon radical and the secondary carbon radical. Contrast this with the chlorination that we just did. Those steps were exothermic. And then the second propagation step is exothermic. And if you calculate the delta H overall, which would be the sum of these two, like we did for the chlorination of methane, the overall reaction is going to come out exothermic. Now, why did we do all of this? Because we need these numbers to build a reaction profile diagram. And then based on that, we can basically go ahead and understand why is bromination selective compared to a chlorination reaction. Okay, so that's why we did this. So we have some of these numbers here. In fact, I think I should have noted those down, but I have the textbook here, so I think I can look at the textbook for the chlorination, -9, -19. Okay, so I'm going to erase this so that we can start building our reaction profile diagram now. Okay. Okay, so, and we're going to build two reaction profile diagrams, one for chlorination and another one for bromination. Okay, so for chlorination, and we will first work on the chlorination because then I want to highlight something so that we don't have to do all of this work for the bromination. Okay, so after the chlorination, we'll be able to like trim out a little bit. So for chlorination, based on what we just did, all the math, it seems like we had reactants. Let's say this is where our reactants are. Our first propagation step, again, we are only drawing this for the propagation steps because that's where the products are formed. Our first propagation step for chlorination was exothermic for both the primary and the secondary carbon radical. So if this is where the reactants are, or maybe since both steps are exothermic, it's okay, we can keep it here. Let's say this is where the primary carbon radical is. Okay, so it's slightly exothermic. The secondary carbon radical was a little bit more exothermic because the numbers were -9 kilojoules per mole and -19 kilojoules per mole. So -9 and -19. So we're just trying to show that here. Okay, so the red, okay, the black trace is for primary, and the red trace is for secondary. Okay, so that means our reactant start here, or maybe we can go ahead and finish it up, and then overall the reaction was exothermic because the second propagation step was also exothermic. I kind of blanked out on what those numbers were, but I think they were like -119 or something like that, but they were again very close. Okay, so let's say that's what one of them is, and this is the other one. I think that was pretty much what we saw. Now it could be the other way around, but that's what we have. So Now what's happening here is then our reactants start here, they go up a transition state on the primary, for the primary carbon radical intermediate. That means the reaction profile for the formation of the 1-chloropropane. Okay, so this is formation of 1-chloropropane, and this is formation of 2-chloropropane. Okay, so it starts with the reactants, slightly exothermic, becomes a product, becomes the intermediate, and then from here goes up a transition state and then becomes product there. So that's what the trace is. Now, the same reactant, the chlorine and the propane, it can go to the secondary carbon radical. Now, since the secondary carbon radical is lower in energy, it's going to go up a trace again, but that trace is going to stay below the initial trace because it's going to a lower intermediate. And then it's going to go down like that and then become product. So that's what we have here. Okay, so that's what the trace should look like. Now, based on this trace, what we can see is that the rate determining step, okay, and again, remember that the rate determining step has the highest activation energy. So whichever step has a higher activation energy, that is our rate determining step. And so based on this profile, what you can see is, or maybe my trace is not the best, but it turns out the first step here, okay, for this reaction, the first propagation step is the rate determining step. Okay, that has a higher activation energy. Okay, this has a higher EA. And so what that means is, as far as the reaction is concerned, that is the most important step. Okay, that's the most important step. The second propagation step is not as important. And so what we can do is we can actually ignore the second propagation step for further consideration, like from our further consideration, because it's not the difficult thing to do. So rate determining step means it is the rate limiting step. That means it controls everything else. It is the most difficult thing to do. If the reactants can get over that activation hill, then they can basically get over everything else. So that's the most important thing to do in the reaction, or the most difficult thing to do in the reaction. So that's why it's called the rate determining step. And so since once the reactions can get over this hill, they can pretty much get over everything else, we can ignore the other portions of this reaction profile diagram. So that's why I wanted to do this chlorination first, just to show you an overview of this, because based on this, now we can basically ignore the second propagation step. Okay, so if I if I adjust for that, and if I actually redraw everything so that we are only looking at the second propagation step. Okay, so first propagation step is rate determining. It's also called the rate limiting step, is the rate determining step. Hence, it determines, generally now, this is not always the case, but generally it determines the reaction outcome. Okay, So it is what determines the reaction outcome. There are reactions where that is not the case. There are other parameters that need to be considered, but generally the rate limiting step is what controls the outcome of the reaction, okay, generally. So that is why it determines the reaction outcome. So we can ignore the second propagation step. You can ignore the second propagation step. So I'm going to adjust this graph, okay, because we don't need the second propagation step here. So we can only focus on the first propagation step for chlorination and bromination and understand why bromination is more selective. That is what we're trying to understand here. Why is bromination a more selective reaction? Okay, so let me go ahead quickly fix this. I'm going to erase that as well. And now I can draw this a little bigger, slightly bigger. Okay, so this is chlorination. We are only focusing on the first propagation step. Okay, just on the first propagation step. So for chlorination of propane, we have CH3, CH2, CH3, propane plus a chlorine radical in the first propagation step. This is what our reactants are. And then the reaction is exothermic. So let's say this is where we make HCl plus the primary carbon radical. And this is where we make HCl plus the secondary carbon radical. Okay, so now basically zooming in, focusing on that step, on those steps. So first propagation step, propane can react with chlorine radical to give HCl and the primary carbon radical, or propane can react with chlorine radical to give us HCl and the secondary carbon radical. Oh, I think I wrote them really big. I don't have enough space for my bromination now. So this is where we have HCl plus CH3, CH2, CH2 radical, and we have HCl plus the secondary carbon radical. Okay, now for bromination, this profile would look something like this. So this is propane plus bromine radical, so reactant from the first propagation step. And the first propagation step for bromination is endothermic, okay? So let's say this is where HBr plus the primary carbon radical is, okay? And this is where HBr plus the secondary carbon radical is. They're both endothermic compared to, or they're both endothermic steps. So now what's happening is the reactants go over a transition state, become products. So propane reacts with bromine radical to form HBr and the primary carbon radical, or propane reacts with bromine radical to give HBr and the secondary carbon radical. This is what the profile should look like. Now, they're definitely not to scale. I can see it on the screen, you know, they look very different, but I think it does serve the purpose. So now what we can do is we can actually come back and think about these transition states, okay? Because this is an exothermic process, what we can say is that this transition state here, okay, it is exothermic process. Transition state is closer in energy to the reactant. That means the transition state should look more like the reactant. Reactant is when we have propane and chlorine radical. So I think the transition state for this process is going to look something like this. CH2, H, chlorine, radical nature. So what I've done is I've shown dotted bonds between the carbon and the hydrogen, the primary hydrogen, and between the hydrogen and the chlorine to say that these are the bonds that are breaking or forming. But I've put the hydrogen closer to the carbon to suggest that this transition state is more like the reactant. And in the reactant, we have propane and a chlorine radical. So the chlorine radical is farther away. Similarly, this transition state here should look something like this. CH3, CH, CH3, H, Cl. And again, what I've done is I've placed the hydrogen closer to the carbon because this is an exothermic step. Transition state is closer in energy to the reactant. That means the structure of the transition state should also resemble the reactant. And in the reactant, we have propane plus chlorine radical. That is what we have. But this transition state also has some radical nature to it, okay? Because this primary carbon radical is starting to form. The secondary carbon radical is starting to form. That is what's happening here. Now, when we go to the bromination example, these are both endothermic steps. The transition state is now closer to the product, okay? Which means the transition state is closer to the product. That means this transition state should now look more like the product. So I'm going to represent that by drawing something like this. And what I've done here is I've done the exact opposite of what I did here. Now the transition state is more like the product. In my product, there's HBr and there's a primary carbon radical. So I've put the hydrogen closer to the bromine to say that HBr is almost formed, and I've basically put a bigger distance or like bigger separation between the carbon and the hydrogen to say that the carbon radical is also almost formed. Similarly, for the secondary carbon radical, the transition state should look something like this. Okay. Again, bigger separation between carbon and hydrogen to say that this bond has almost broken. Okay, it's done. HBr closer together to say that it's almost HBr here. Okay. Now this picture here, it basically captures the reason. Okay, it kind of explains why bromination is more selective. So if we look at the two two profiles here for chlorination and bromination. And also remember that we are focusing on the rate determining step now. That means the most important step in the reaction. This step is going to define the outcome of the reaction. Now, for chlorination, the transition state leading to the transition state that belongs to the rate determining step is still like the reactant. Okay, that means nothing much has happened. The bond between carbon and hydrogen hasn't broken yet. The bond between hydrogen and chlorine hasn't broken yet. So that means these transition states, both of these, they don't have a lot of radical character to it, because the product is either a primary carbon radical or a secondary carbon radical, but they don't have a radical nature or a significant radical nature to them, which means they don't feel that different from each other, because based on the stabilities of radicals, remember that a secondary radical is more stable than a primary radical. But these transition states, both of them, they don't really feel that difference because the radical hasn't formed yet. They are still, both of them, they're both still mostly like propane and a chlorine radical, which is the same then. Okay, so they don't really feel a difference. So they are very similar to each other, and that's why when we get to the products, we get a very similar product distribution. We get that difference of 20%. So 60% of the secondary product and 40% of the primary. Now, why do we get more of the secondary or the 2-chloropropane product? That is also in this plot, because notice how the path or the reaction profile leading to the secondary radical and then to the 2-chloropropane has a lower activation energy. So that means it is kinetically the more favored product. And in fact, in the end, it is also thermodynamically the more favored product. Okay, so both kinetics and thermodynamics are favoring the 2-chloropropane product. Okay, but there isn't a significant difference because the transition state for the rate determining step is exactly, it's not exactly the same, but still it's very similar for both of them. Now, when you go to the bromopropane case or the bromination example, now the transition states are more like products because it's an endothermic step, which means in this transition state, the primary carbon radical has formed significantly. And in this transition state, the secondary carbon radical has formed to a significant extent. Okay. And now, since the secondary carbon radical is more stable than a primary carbon radical, this transition state is feeling very stable. Okay. It is going to be significantly, compared to this one, lower in energy. And I tried capturing that to some extent by showing a difference. So this is the delta EA between the two steps, the difference in the activation energy for the two steps. And this is the delta EA in the bromination example. And notice how this delta, the difference in activation energies, which is kind of representative of the how stable the transition state is, significant here. And so now, since in bromination, the pathway that leads to this secondary carbon radical is stable, relatively more stable compared to the pathway that leads to the primary carbon radical, we make a lot more of the secondary carbon radical. And if there's a lot more of this formed, and then the second step is again exothermic, okay? So it goes, or it gives you a more thermodynamically stable product. It basically makes a lot more product. And so that is why we get a higher ratio of the 2-bromopropane, because it is formed through a pathway which is very relatively more stable, significantly more stable compared to the pathway that leads to the 1-bromopropane. Whereas here, there isn't a significant difference in energies between these two pathways, so both products are formed in almost equal amounts, but the 2-chloropropane is favored because it's a kinetically and thermodynamically more stable product, if I'm right. I don't remember those numbers, so you might want to verify if it is thermodynamically stable also, but that is what you're seeing here. So this is basically an application of the reaction profile diagrams and everything that we saw in chapter 6. Okay, so that's where we're going to finish this video. I know it's a long video, maybe go through it in chunks, but it's a very important concept that you're going to use throughout organic chemistry when we try to understand why a reaction is favored or why a product is favored in a reaction. So that's a very important concept there. Okay, so this explains why this happens and why bromination is very selective. The key here is bromination is selective. Okay, in a subsequent video, we're going to do a few examples to write products from these reactions, from both chlorinations and brominations. Okay, thank you so much.